In this video, we'll explore joint and conditional probability models for discrete random variables. To begin, a joint probability model describes the simultaneous behavior of two random variables x and y. When x and y are discrete, their joint model is defined by their joint probability mass function, or PMF. This joint PMF is denoted using two subscripts, x and y, to indicate the two variables of interest. Its support consists of possible pairs of outcomes little x and little y. By definition, the joint PMF at the pair little x and little y is the joint probability that random variable x equals little x and random variable y equals little y. In shorthand, we can express this joint probability using a comma between these two events of interest. Like marginal or univariate PMFs, joint PMFs have to satisfy a couple of properties in order to be valid. First, since the PMF is technically a probability, it has to be non-negative for all pairs x and y. Second, it has to sum to 1 across all xy pairs. This is analogous to the PMF of x alone summing to 1 across all values of x. Consider an example. Let two discrete random variables x and y have the following joint PMF. P of x, y equals 2x minus y plus 3, all divided by 36, where x and y must both be either 0, 1, or 2. Thus, we can use this formula to fill in a probability table for the possible joint outcomes of x and y. For example, to calculate the probability that both x and y equals 0, we can plug in x equals 0 and y equals 0 into the joint PMF. The result is 2 times 0 minus 0 plus 3, all divided by 36, which simplifies to 3 out of 36. Similarly, to calculate the probability that both x and y equal 1, we can plug in x equals 1 and y equals 1 into the joint PMF. The result is 2 times 1 minus 1 plus 3 divided by 36, which simplifies to 4 out of 36. We can do the same thing for all possible pairs of x and y values, filling in the inside of the probability table. Once we fill in the inside of the table, we can calculate the sum of each row and the sum of each column. And finally, the grand total equals 1, confirming that this is a valid PMF. Though this table summarizes the joint behavior of x and y, we can also use it to explore their marginal behavior. For example, the sum of the first row indicates that there's a 6 out of 36 probability that x equals 0. Notice, though, that this probability that x equals 0 is actually the sum of 3 joint probabilities, calculating the probability that x equals 0 with y equals 0, or y equals 1, or y equals 2. This result is part of the law of total probability. Now, rewriting these specific probabilities as their corresponding joint and marginal PMFs, what we've shown is that the PMF of x evaluated at 0 equals the sum of the joint PMF of x and y at x equals 0 and y equals 0, at x equals 0 and y equals 1, and at x equals 0 and y equals 2. In shorthand notation, the PMF of x at 0 is the sum of the joint PMF at x equals 0 and y equals little y across all possible y values, that is, y equals 0 to y equals 2. In general, by the law of total probability, we can get the marginal model of one random variable by summing the joint model across all values of the other random variable. For example, the PMF of x is the joint PMF of x and y summed across all y values. That is to say, the probability that x equals little x is the combined probability that x equals little x and y equals little y across all possible y values. Similarly, the PMF of y is the joint PMF of x and y, summed across all x values. That is, the probability that y equals y is the combined probability that y equals y and x equals x across all possible x values. Let's apply this property to our example. Looking at the column sums alone, we can build a table for the PMF of y. Y equals 0 with probability 15 out of 36, y equals 1 with probability 12 out of 36, and y equals 2 with probability 9 out of 36. We can also build a formula for this PMF using the fact that the PMF of x is the joint, or the PMF of y, rather, is the joint PMF of x and y, summed across all possible x values. Thus, P of y is the sum of 2x minus y plus 3 divided by 36 for x equals 0 to x equals 2. Next, we can plug in x equals 0, x equals 1, and x equals 2 into our formula and add up the terms. The result simplifies to 15 minus 3y divided by 36, where again y can be 0, 1, or 2. Finally, notice that our formula for the PMF of y only depends on y, not x. Mainly, a model of y alone doesn't use any information about x. Thus, if our answer still had an x in it, it would be a signal that we made a mistake somewhere in our calculation. Similarly, we can prove that the PMF for x alone is 6x plus 6 divided by 36, which only depends upon x. Now I encourage you to pause your video to confirm this result. We have one last type of model to consider. In addition to a marginal model for one variable alone and a joint model for two or more variables together, a conditional probability model summarizes how one variable depends on another. For example, the conditional probability model of x, given the information that y equals little y, is defined by conditional probabilities. To this end, as we learned earlier in this semester, the conditional probability that x equals x, given y equals y, is their joint probability divided by or relative to the marginal probability that y equals y in the first place. Or using formal notation, the conditional PMF of x given y equals the joint PMF of x and y divided by the marginal PMF of y alone. This formula indicates the importance of tracking and using subscripts. X given y indicates a conditional PMF. X comma y indicates a joint PMF. And y indicates a marginal PMF. Of course, this conditional PMF must satisfy the usual properties in order to be valid. In stating these properties and using conditional models in general, it's important to keep the roles of x and y straight. First, we must remember that x is our unknown variable of interest, and so we should treat it as such. Second, since y equals little y is known or assumed information, it's important to recognize y as a constant or a known data point. Keeping these rules in mind, the conditional PMF of x, given that y equals y, can vary across different values of x and must be non-negative for any x. Again, this is a model of the unknown random variable x. Further, the conditional PMF must sum to 1 across all possible values of x. Again, y is a constant here, so it doesn't make sense to sum the PMF across y. Let's apply this result to our example. Recall the formulas for the joint PMF of x and y, and the marginal PMF of y alone. By definition, the formula for the conditional PMF of x given some outcome y equals little y equals the joint PMF divided by the marginal PMF of y. Plugging in the appropriate formulas, we get 2x minus y plus 3 divided by 15 minus 3y for x in 0, 1, or 2. We can use this formula to obtain a more specific conditional PMF of x for any specific value of y. For example, if we learn that y equals 0, then the conditional PMF of x is obtained by plugging in y equals 0. After simplifying this equation, we're left with 2x plus 3 divided by 15 for x in 0, 1, or 2. It's important to notice here that our conditional PMF of x given this specific constant y, here y equals 0, it only depends on x, not y. If our answer still had a y in it, it would be a signal that we made a mistake somewhere in our calculation. Finally, we can use this formula to calculate a conditional probability table for x given y equals 0. Importantly, all of the probabilities here are non-negative, and they sum up to 1 across all possible outcomes of x equals 0, 1, or 2. Taking a step back, we now have a marginal PMF of x alone, as well as the conditional PMF of x given y equals y. And notice that these formulas differ, signaling that information about y can change our understanding of x. That is, we say that x and y are dependent, not independent random variables. In general, recall that we said two events A and B are independent if and only if information about B doesn't change our understanding of A. That is, the conditional probability of A given B equals the marginal probability of A. Similarly, two random variables x and y are independent if and only if information about y doesn't change our understanding of x. That is, the conditional PMF of x given y equals the marginal PMF of x. Equivalently, we learn that events A and B are independent if and only if their joint probability is the product of their marginal probabilities. Similarly, random variables x and y are independent if and only if their joint PMF is the product of their marginal PMFs.